This topic's digital data communication techniques. So to date we've looked at signals, and especially last topic we looked at how to encode data as signals, whether we have digital or analog data. And digital or analog signals, we have 4 different approaches. We know something, that when we transmit our signal, whether it's analog or digital, what's received is going to be different. The signal gets weaker over distance and we have noise. The problem that arises is that if what's received is not what is transmitted, as a result there can be errors at the receiver. This topic's going to look at how do we detect and correct those errors, but we're going to focus on, as the title suggests, digital data. The cases where we're sending bits. So we have bits, zeros and ones. I want to communicate bits from my computer to another. I may use analog signals or digital signals. We don't care so much in this topic. What happens if there are errors? That's what we'll cover here. First, something quick, or a quick description of bit errors. So now we're dealing with transmitting bits as our data. If we transmit a bit 1 and it's converted into a signal, and the receiver receives that signal and interprets the bit as bit 0, that is a bit error. If we transmit 1 bit, receive the other, something's gone wrong. Why would we do that? Well, if we transmit a bit and there's noise in the system, then it may make the decision made by the receiver to be incorrect. It thinks the level is high when in fact the level was low. So we get bit errors. We can have single bit errors when we have, which always dealing with transmitting a sequence of bits, hundreds, thousands, millions of bits in a sequence. Single bit error, if we have, for example, random noise, may cause just 1 bit to change. I send 100 bits. The 51st bit is received in error. The other 99 bits are received correctly. There's a case of a single bit error. Often caused if we just have some noise in the system that's random, something that we cannot control. In some cases we may get a burst of errors. I transmit 100 bits and there are 10 or 20 bits in sequence which are all in error. A burst of errors. A group of bits which are near each other that are all affected are in error. It may be caused by some impulse or some spike due to an electrical fault, some problem with the wireless communications. The point is, if we have a burst of errors, then normally it's affected by the speed at which we're sending. The data rate. For example, we have some noise and a burst of error may be caused by a large impulse of noise. That is, if this is showing the noise in the system, it's quite small most of the time. The smaller the noise, the less chance of bit errors. And then for some period of time, there's an impulse of noise. I don't know, some electrical fault in our communication system, a lightning strike, some computer fault. So there's a large amount of noise, and then it comes back to very small. This may cause a burst of errors. And importantly, the faster we're sending bits, the more errors are going to be occur. The more bits will be affected. We know that the more noise, the more chance of error, because we send some signal. This changes the signal from the signal transmitted compared to the signal received. This large amount of noise causes a large change, which may mean if our bits transmitted were all at a low level, if we were transmitting some digital signal if this was our example digital signal transmitted, the received signal would look similar, except there would be a small amount of noise. But at this point, we were transmitting at a low level, but because of this large amount of noise, our received signal will be something like this. So where there's a large amount of noise, we may get the chance, in this specific example, where the levels change. Therefore, we get bit errors. Because if this was representing 0, 1, 0, 1, 1, 1, 0, 0, 1, then what's received? Okay, high level, bit 0, 0, 1, 0, 0, 0, 0. 3-bit errors in this case. Just for that example. Noise, transmitted signal, received signal, where we see that we change the level because of this large impulse of noise. Here's a burst of errors, or a small case of a burst of errors. If we were transmitting faster, more bits per second, we would have more bits impacted by this noise. If my signal, we're going to run out of spaces. If my signal was sent twice as fast, it may not look so good, but we'll explain it in a moment. That is, the red signal is now representing a sequence of bits, but we're sending 2 bits in the same period as in the previous signal. Sending bits faster, double the data rate. Then the noise is going to impact on all these bits. So if this was a bit 0, 1, 0, 1, and so on, the noise, the same amount of noise, would impact on 1, 2, 3, 4, 5, 6 bits. In the previous case, it impacted on 3 bits because we've doubled the data rate. So, normally, one of the trade-offs that we've dealt with, we've talked about the relationship between bandwidth and data rate, noise and errors. The higher the data rate, the more the chance of burst errors. The more errors that can occur due to a burst of, or an impulse of noise, for example. So when we deal with higher data rates, although we want to send at higher data rates, we may be impacted by errors more, and we need to deal with that. Now, the main point that we get here is that if we have errors at the receiver, what do we do about it? The receiver receives this. First, the receiver needs some way to detect that errors have occurred. And once we know that the errors have occurred, correct them where possible. If you receive a sequence of bits, this is the sequence of bits received. Are there any bit errors? The blue sequence up there. Are there any bit errors? Anyone? The blue sequence, 0, 1, 0, 1, so on. Are there any bit errors in this case? This is what's received by the receiving device. You don't know is the answer. There's no way to tell what is transmitted. So the receiver receives a sequence of bits. How does it know if there's any bit errors? Just by looking at this, we have no idea. So what we do is we're going to include some extra information so it makes it possible for the receiver to detect errors. So first thing we need to be able to detect, are there any errors in here? We cannot compare it to what the transmitter sent, because the transmitter may be on the other side of the world. So we need some other mechanism to detect errors. And if we can detect errors, what we'd like to do is correct them. Receive the actual correct bits. How can we do that? So first, how to detect errors. Error detection. The basic process is for the transmitter, or the process we'll talk about, the transmitter to include some extra information with the transmitted data, where this extra information is called an error detecting code. So if we have some bits to transmit, we have the data, the sequence of bits to transmit, and instead of just sending the data, we send the data as well as an error detecting code. Some extra information with the aim we transmit, the receiver receives both the data and the error detecting code. If it's designed in a good way, the receiver should be able to detect if there are any errors in the data. That's the objective, detect errors. If there are no errors detected, we will assume that everything's okay. How that works, this diagram tries to illustrate it. This is the transmitter, this is the steps at the receiver. The transmitter has some data to send, k bits. Has k bits of data. It applies some function on that data. And we'll talk about, we'll give two examples of different functions it can use. There are others. It applies some function and gets some value E, the error detecting code. And it appends, in some cases it can prepend, but it attaches the value of this calculated, of the calculation of the data and the result E. It includes that with the data. So we have k bits of data and n minus k bits of error detecting code. K bits of data and n minus k bits of extra bits. We join them together and we transmit all of those n bits together. We have n bits because this plus this equals n. So we have n bits and transmit those n bits across our link. They go to the receiver. The receiver receives those n bits. It must know where the split is. That is, okay, the first k bits of the data. It takes the received k bits of data, the received error detecting code. It calculates on the received data the same function as the transmitter used, and then compares the value of this function, E, it's actually E prime here, with the received error detecting code. If they match, the receiver assumes everything's okay, no bit errors. If they are different, the receiver will assume that there are bit errors. That's the general approach with error detection. We have our normal data, we attach some extra information. That extra information is chosen such that the receiver can use it to detect if there's any errors in the received data. The specific ways to do it, there are different approaches for error detection. We'll just go through two examples, one in some depth, which is very easy, and just mention a second. The first example is the parity check. You may have covered this in some computer hardware course. It's very simple. A parity check in this simple case is that we append or we include an extra bit and we attach that. We either add it to the end or to the start of our data. And with an odd parity check, that bit is selected, it's either a 0 or 1, it's selected such that the total number of bits, or the total bits, there is an odd number of ones. So, an example. Our original data, as an example, let's say we have k equal to 5. We have a block of 5 bits of data. Let's choose 5 bits. That's the data we want to send. So at the transmitter we take those bits and we attach a parity bit. In this case our error detecting code is just a single bit attached. The size of the parity bit in this case is 1. A 1-bit parity check. What value do we add if we're using odd parity? So we've got 5 bits of data. The scheme on odd parity check is that of the total bits that we're going to transmit, there should be an odd number of ones. So what are we going to do? Count the number of ones, and how many ones do we have? We have 3, so we're going to add 1 parity bit. What's the value? We're going to add 1 parity bit. It's either going to be a 0 or a 1. We add a bit such that of all the bits, we still have an odd number of ones. Let's add it to the end. So in fact, this is the data, this is the error detecting code, the parity bit. What we're going to transmit is the combination of those 5 plus 1 bits, that is the total of 6 bits. Where this is the parity bit. This is the 6 bits that are transmitted. Count the ones, we have an odd number of ones. So the way that we chose this red 0 here is such that when we get this, we have an odd number of ones. So if we already have an odd number of ones here, we add a 0. If we have an even number of ones here, we add a 1. That's a very simple parity check at the transmitter. We'll see how it works at the receiver. So we transmit these 6 bits. We transmit them across our link. Let's assume first there are no errors. That is, the 6 bits which are transmitted are the 6 bits received. The receiver receives 0, 1, 1, 0, 1, 0. The receiver and transmitter know the error detection scheme that they're using. That is, the receiver knows that the transmitter is using odd parity, a 1-bit odd parity check. So the receiver knows, in fact, we have 5 bits of data and 1 bit for the parity check. Is there an error? Well, what the receiver does is counts the number of ones. 1, 2, 3, 3-bit ones. Odd. We know that the transmitter should have transmitted an odd number of ones because we're using an odd parity check. Because in this case we receive an odd number of ones, we assume it's correct. We assume that the bits received, there have been no errors. So that the received data, Rx, this is the received bits, but we know that the first 5 bits are for data, the last bit is for error checking, the parity bit, so we just take the first 5 bits. and we've received the data and we've checked the data whether there's any errors. That was in the case that what was received was identical to what was transmitted. That is, there are no errors in the link. Imagine the link is from here to here. Let's try another case. Let's say we transmit those 6 bits, but the second bit is received in error. The receiver doesn't know that yet, but we transmit these over the link. There's some noise. As a result, what's received is these 6 bits. There's some error in the link such that the second bit is received as a 0 instead of an actual 1. The receiver doesn't know that. This is just 6 bits it's received. It applies the parity check. Count the number of ones. Even. Error detected. The transmitter must transmit an odd number of ones. We received an even number of ones. Hence, something's gone wrong. And that's the process in work. That is, the error has been detected. Very simple. So in this example, I assume that there was 1 bit error. Of these 6 bits transmitted, the second bit was received in error. The receiver counts the number of ones received. It should be odd, but in fact in this case it's even. Therefore we assume that there's some error has occurred and we've detected an error. We haven't detected where the error is. We don't know which bit is in error, but we do know in this block of data there is some error. And then we could later do something about that to try to fix or correct that error. But that's something we'll cover in the next part. So in fact there's no data received in this case. We receive something that's in error. We'll need some other mechanism to try and correct it later. As a third example. We transmit these 6 bits. The first 2 bits are in error. So we transmit 6 bits. First 2 bits are in error. So we'll get 1, 0, 1, 0, 1, 0. What happens? What happens at the receiver? The receiver does the check and determines it's correct because we have an odd number of ones. We have 3 ones. What's wrong? So, the receiver, if we have an odd number of ones, it assumes everything's correct. If we have an even number of ones, it assumes everything's incorrect, or there's something incorrect. In this case, we have an odd number of ones. Therefore, we'll assume that the received data is correct. The received data is 0, 1, 0, 1, 0, 1. Is the received data the same as the transmitted data? No. This is where the error detection has failed. It didn't work. That is, error detection is not perfect. In this case, we had bit errors, but the scheme that we used did not detect those errors. It missed them. As a result, we transmitted some data. The receiver received data which is wrong, or thinks it's received this data, but in fact that's incorrect. Why? Because with this single bit parity check, if we have 2-bit errors, we will miss the errors. We'll see if we have any single bit in error, we'll successfully detect. If we have any 2 bits in error, we will miss that. We'll make the wrong assumption. 3 bits, okay. 4 bits, not okay. That is, a single bit parity check is very simple but not very effective in some cases. It can only detect an odd number of bits in error. So we had 3 cases. In general, we have 3 cases that can be the outcome of error detection. The 3 examples we went through illustrated the 3 possible cases that we're going to have. At the receiver, we use our error detection scheme to make some assumption or some decision. Is the data we receive correct or not? The 3 possible outcomes are: the receiver makes an assumption that there was no error in the data transmitted, and that's the correct assumption. That was the first case we went through. Transmitted the data, there was no error in the transmission, the receiver received it, counted an odd number of ones, made the assumption that there was no error, and the received data was matching the transmitted data. That is, we'll say that the receiver assumed that there was no error, and that was a correct decision. The correct data was received. So that's one case. The second case we went through, if there is a transmission error, we transmit some data, there's an error in the link, we receive the data, the receiver detects an error, that is, assumes some error has occurred. As a result, there's no data received, or we ignore the data received and we have to correct it some other way. That was the second case. These are both, these are both successful outcomes of the error detection. In the first case, there was no error and the correct data was received. In the second case, there was an error, the receiver detects that, that's a successful outcome. If there's an error and we detect it, that's good. The third case, which we just went through, there are errors in the transmission. The receiver assumes that there are no errors. In this case, we received this, counted an odd number of ones, therefore assume no errors. The data received is incorrect. The data that we receive here does not match the data that was originally transmitted. This is an unsuccessful outcome of our error detection scheme. And in practice, most or any error detection scheme, we make a trade-off between these 3 cases. We'd like to minimize the chances of this happening. So there are different algorithms for error detection, and we can change some parameters to minimize this. But we cannot, in practice, it's always a chance that these cases will occur. So the parity check is just one simple example, but it's not very effective. If we have multiple bit errors, it will not detect them. So there are other schemes to try to detect what happens if there are 2 bits in error. Can we detect that? Any questions on the parity check before we move on? Make sure you know how the transmitter determines the parity bit. But more importantly, make sure you know what the receiver does when it receives that data. Try for the next 5 or 10 minutes. Let's go. You will go through an example. Let's say we have a character, an ASCII character to transmit. We want to send my name, Steve. All right, the first character is S. So what we do to transmit this from the transmitter to the receiver, we're not sending letters, we're going to send bits. We'll convert this digital data, the S, into a sequence of bits. And the ASCII table is one way to do that for us. So if we have the letter S, if we look at the ASCII table, this is one of our other lecture notes, uppercase S is in fact represented by 7 bits, 101, 0011. In fact, because I have a different example, let's try a different letter. Letter Q. The only reason is because I have the solutions for letter Q, not S. Let's try the letter Q instead of S, where Q, lowercase q, if we want to transmit that to the other side, we'll send the 7 bits of data. Q is here, 111. Q 111 0001. So that's the data we want to transmit. So the question, instead of S, let's assume Q. Assume the character Q is to be sent using odd parity check. Odd parity check means that we should have an odd number of ones in the data that we transmit. And the receiver should receive an odd number of ones. Odd parity check. First question, what is transmitted? Second question, what happens if the last bit is corrupted? And what about the last 2 bits? And in this case, let's assume the parity bit is the leftmost. In the previous example, I added the parity bit to the end. In this example, add the parity bit to the start. So it's going to be parity bit followed by 7 bits of data. What is transmitted? Quickly determine the answer. What is transmitted? We have 7 bits of data, and we have a 1-bit odd parity bit. The parity bit comes first, followed by the data. What's the parity bit? What's the value?
1.
Why? I'm not saying it's correct or incorrect. Why did you give that answer? You've got a 50% chance of being correct, 1 or 0. Did you just guess or did you know?
Because it's odd.
Because what's odd? Because when you add a bit 1, the total number of ones will be odd. We have an even number of ones already. We add a bit 1, so we get an odd number of ones. So the 8 bits that we transmit are here. The first parity bit, which is bit 1, and then the 7 bits of data, such that the total number of ones is odd. We transmit that. The receiver receives something. In this case, across our transmission link, what happens if the last bit is corrupted? We transmit these 8 bits, and when I say first bit, I mean the leftmost, and last bit, the rightmost, to keep things simple. What if we transmit this, the last bit is in error, what does the receiver do? Try. Why is it so hard to see? I'll fix that. Determine what the receiver does in this case. Everyone's got the outcome? What happened? What happens at the receiver? Receiver receives 8 bits. What does it do with them? 4 ones are received. Okay, correct. And that means, what does the receiver do or assume? Assumes error. Why? Because it's an even number of ones. Okay, so what's received? If they were the 8 bits transmitted, that's what's received. The last bit is in error or corrupted. The receiver doesn't know that. This is just the bits it receives. It does its check. We count the number of ones. We have an even number. And using the odd parity check, that means there's an error. Assume an error. And of course there has been an error. So this is a correct, although we've got an error, it's a correct algorithm of a correct outcome of our error detection algorithm, because there was an error and we detected that error. So the error detection has been successful in this case. And then we'd use some other approach to maybe try and fix that error. And I think you can quickly know what will happen if the last 2 bits were corrupted. What happens? Last 2 bits are corrupted. So we transmit not those 8 bits, but the last 2 bits are received in error. What's the receiver do? Calculate the answer. Some people have got it. Everyone's got the answer? Very easy. You know what's going to happen? Exam on Monday. A question on this. There won't be a question on this because this is too easy. The questions will be harder. Okay? So if you know this, okay. But we've got harder things to cover soon. Any questions? It's all okay. What happens at the receiver? What do we receive? The last 2 bits, so this is what was transmitted. What is received if the last 2 bits are corrupted? Incorrect data. Why? The comment was incorrect data because there's an error. Okay, but remember that transmitter and receiver are independent. The transmitter is one computer connected via a cable to another computer. What the transmitter sends into the cable, the receiver doesn't know. All the receiver knows is what it receives. If the transmitter sends a signal into the cable and there's some noise and the receiver receives something different from what the transmitter sent, the receiver doesn't know it's different. The only way it can detect the error is using such an algorithm as the parity check or another error detection algorithm. So we don't know if there's any errors. We need to look what is received. Last 2 bits in error, this is what's received. Last 2 bits were alternated or swapped in sign. And how many ones? Even number, an odd number of ones. And we assume no error. Whenever there's an odd number of ones, we assume everything's okay. Even number, assume an error. Assume no error, therefore the received data, we throw away the first bit because we know that's the parity bit, and we take the last 7 bits. The received data, we know that the first bit is the parity bit, so we just take the last 7 bits. This is what we get. It does not match the transmitted data. So this is the case where we assume that there was no error, but in fact there were errors. We made a mistake. The error detection did not work in that case. Any questions? So all the receiver does is count the number of ones in the parity check. Error detection with parity check is not very successful because we saw if there were just 2 bits in error, it didn't work. If there was 1 bit in error, okay, 2 bits in error, unsuccessful. So there are other algorithms. You would have heard of it, CRC check, or cyclic, not CRC check, cyclic redundancy check, the CRC error detection algorithm. Parity checks are not good when there are multiple bits in error. CRC is a much more powerful and very commonly used error detection scheme. We're not going to go through it. We're going to just mention the name, and just because of time we're going to skip over CRC or how the algorithm works. But it's a very common one, and the point is it's better than parity because even with multiple bits in error, it will successfully detect them. Our parity check, when there were 2 bits in error, did not detect that. With a CRC we can. And in general, in fact we can improve the parity check. The more bits we have in the error detecting code, the better we can detect errors. With the parity check, with our CRC, the same concept applies. We have k bits of data. We have an error detecting code of n minus k bits, and we transmit n bits. The larger the error detecting code, the better error detection capabilities we have. In fact, you can have more than a single bit parity check. You can have a 2-bit parity check or a 3-bit parity check. And we can detect more errors in that case. So the larger this compared to the data, the better an algorithm is at detecting errors, but it means the more bits we transmit. To finish on error detection, data rate, my link between transmitter and receiver, assuming there are no errors, but we use the 1-bit parity check, my data rate of the link is 8 megabits per second. What's our throughput? Assume we're in the perfect case, there were no errors, but we still use the 1-bit parity check. I can send 8 million bits per second. How fast do I receive data? Anyone have the answer? You've got it? Can help him? Can send 8 million bits per second. But with our parity check scheme, I have 7 bits of data. I add 1 parity bit and transmit all 8 bits. Therefore, the rate at which I send real data is what? Seven bits of real data, but transmit 8 bits over the link. Who's got an answer? Seven megabits per second. I'm sending 8 million bits per second, but of what I send, we actually send 8 bits at a time. 8 bits. But only 7 bits are real data. The other bit is a parity bit. So even though I'm sending 8 million bits per second, 7/8, running out of space, 7/8 of that is real data, 1/8 is the parity check. The throughput is a rate at which I receive the real data. I'm sending 8 million bits per second, 7/8 of that is 7 megabits per second. So there's an overhead. This extra bit here is an overhead incurred. The more bits we add in the error detecting code, the lower the throughput will be. So the throughput in this example would be 7 megabits per second. If I had 4 bits of real data and 4 bits of error detecting code, then the throughput would be 4 megabits per second, because we have, of the total 8 bits, only 4 of them are the real data. So the larger the error detecting code, the lower the throughput. But the larger the error detecting code, the better it is at detecting errors. So there's a trade-off that comes up. We will recap on that trade-off at the end of these lecture notes. Error detection is easy, but not sufficient for our system to work, because what do we do when we detect errors? The receiver knows there's an error, it detects an error. We want to fix that error. We'd like to receive the correct bits. So we in fact need error correction. And there's 2 basic approaches. When the error is detected at the receiver, there's 2 things it can do. The first approach is to ask the transmitter to send again. Transmit the bits, detect an error, say please send again. What you just sent me was in error, transmit again. And hopefully the second time there will be no noise and we'll receive the bits correctly. If not, we'll say please send again, and we may keep trying. This is a retransmission scheme, and we're going to spend a lot of time covering up after the midterm. we'll see the exact ways to ask for the retransmission, but that's one way to correct errors. It doesn't work in some cases, or it's not very efficient in some cases, especially wireless and satellite links where there are a lot of bit errors. An alternative approach is called forward error correction, which is all we'll concentrate on today before the midterm. What the sender does is it includes some extra information with the aim of when the receiver receives the bits, if there's an error detected, it can actually determine what the correct data was. It can correct the errors without asking for a retransmission. Before we look at the concepts, let's use an example to explain how it works, or show how it works. There are different error correction schemes, or forward error correction schemes. We'll go through one in this topic. And before, we'll use the example to explain how error correction works. This is a simple forward error correction scheme, and it's going to use the concept called Hamming distance. You know Hamming distance? You've covered it in a different course? Yes? You remember Hamming distance? Yes. Maybe, maybe not. You may have covered it in a computer hardware course. Don't worry, we'll cover it. The Hamming distance is very simple. You have two sequences of bits of the same length, same number of bits. The Hamming distance between those two sequences is the number of bits that differ. Best to look at it, so in the example, two sequences of bits, V1, 6 bits. Look at that, yep. And V2, another sequence of 6 bits. The Hamming distance between, so it's a measure of distance, how close the two sequences are between V1 and V2. We simply look at the bits in order of both sequences, and if they differ, we count 1. If they don't, we move on. That is, the two first bits differ, so that's 1 bit in the sequence that's different. These are the same. These two are different, so there's 2 bits, or a distance of 2. The same, different, the same. If you cannot see that, that's 3. The distance between these two sequences of bits is 3, a Hamming distance of 3. Any problems with that? So take any two sequences of bits, same length, you can determine the Hamming distance between them. It's a measure of how close the two sequences are. Quick check. 2 more sequences. What's the distance between them? 0, they're the same. What's the distance between them? 4. Okay, so the distance is larger when they are not the same. So the further they are apart or further they differ, the larger the distance. So it's a measure of closeness between sequences of bits. Now that's not part of, that's just a general concept, it's not part of all error correction schemes, but it's what we're going to use in our example, forward error correction. What we do with forward error correction is that we take the data that we want to transmit, and instead of sending that data, we send a code word which represents that data. So we have some data to transmit. We have a mapping from data to code words, such a table. We transmit the code word to the other side, And the receiver uses that code word to detect if there are any errors, error detection. If there are errors, it will try to correct. Find out what the original data was. So let's use use this example to go through and explain how that works. So the next few slides are the example that we'll go through. This one and the next, I think, 3 slides. But on the screen I'll just leave this up here so that we can refer back to what we have here. So both the transmitter and receiver have this mapping of data to code word. And the code word is longer than the data. So in this example that we're going through, we have 2 bits of data, k equals 2, and a 5-bit code word. So there are 4 combinations of data possible with 2 bits. There are 32 possible code words. We only use 4 of them. Okay, we're only using these 4. The selection of the 4, there are good ways to select the 4. In this case, we just got an example. 000 is represented by the code word with 5 zeros. 01 with this code word, and so on. At the transmitter, we have some data. I'll denote it as TX data. So we want to send 2 bits to the receiver. Those 2 bits are 0, 1. So we use our mapping and we determine the corresponding code word. So we look up in our table, data 01 maps to code word 00111. So to transmit this data, we don't actually send those 2 bits, we send these 5 bits. We send them across our link. The code word is transmitted across the link. And let's look what happens at the receiver. Note that the transmitter and the receiver both know this table. They both know this mapping of data to code words. First case, which is on the next slide, assume there are no bit errors. That is, if that's the transmitted code word, the received code word is identical. We receive what was transmitted in this example. So what the receiver does is that it takes the received code and compares to the valid code words in the table. So we now distinguish between valid and invalid code words. In this example, there are 4 valid code words. The 4 listed here. You don't have to write them out. And the other code words are invalid. How many are there? How many invalid code words? More? 28. The code word is 5 bits in length. With 5 bits we can have 32 possible values. 4 of them are valid. The remaining 28 we'd say are invalid code words, whatever they are, which I'm not going to write them all down. That's one of them. There's 4 valid and 28 invalid, because there are 32 possible with a 5-bit number. The valid ones are known by the transmitter and the receiver. They are selected. So what the receiver does when they have a received code word, they check if it's valid. And in this case, the received code is a valid code word. That is, the received code word matches this valid code word. In this case, we assume no errors. Why? Because we know that the transmitter must have transmitted one of these 4 code words. All the transmitter does is takes the data it wants to send and transmits the corresponding code word. So the transmitter transmits one of these 4 values. If we receive one of those 4 values, then we'll assume nothing went wrong. We expect to receive one of those 4 values. So this is a case we assume no errors. We take the code word received, map it back to the data. So the received data, if this is the code word, we look in the table, it gives us 0, 1. Is that correct? Yes, we transmit data was 0, 1, receive data 0, 1. Everything's fine. Of course, that was the case where there were no errors in the transmission. Make sure you've got that down, because we're going to wipe it off in a moment. Any questions? Transmitter takes the data, maps to a code word, sends the code word. Receiver checks if it's valid. If the code word received is valid, then you immediately get the received data, which was this case. Let's try another case. Here we assume no errors. Let's assume, where are the errors? Let's assume there's 1 bit in error. Let's assume we transmit these 5 bits. One of them is in error, and let's say it's the 3rd bit. I'm about to remove this. Any questions before I do so? Okay. Questions? All right. We have time. That was the easy case. Everything worked because there were no errors. I'll leave this here. The set of valid code words is always these 4. That's part of the algorithm in this case. We transmitted the bits 0, 0, 1, 1, 1. There's a bit error. Something goes wrong. The 3rd bit is in error. So in fact we'll receive the bits 0, 0, 0, 1, 1. Compare the transmitted code word to the received code word. This bit is in error, the 3rd bit. So now, the receiver takes the received code word, compares it to the valid code words. Is the received code word valid? Anyone? Is the received code word a valid code word? Invalid. It's not in that set of 4. That is, it's not here. So it's an invalid code word. Which means we've detected an error. Our error detection has taken place here. Because if we don't receive one of these four, we know that the transmitter transmitted one of these four, something's gone wrong between the transmitter and receiver. So we've got error detection here. But we want to correct that error. We'd like to know what was the actual transmitted data. So now we take the received code word and compare it to the four valid code words and compare it in terms of distance or Hamming distance. So we take the received code word, compare it to each of the four valid code words and find their distance. The first valid code word and the received code word, what's the distance? Received, valid code word 1, what is the Hamming distance between them? 2. 2 bits differ. The received code word and the second valid code word? 1 bit differ. That is this one and this one. So I'm comparing the received with each of these four values. The received and the third valid code word. The received code word and the third valid code word. 3. First bit differs, second bit differs. The fourth bit is different. There are 3 bits that are different. And the received code word and the last valid code word. 1, 2, 3, 4 bits are different. The Hamming distance between this and this is 2. Between the received code word and the second valid is 1. Received code word and the third valid code word is 3. And the last is 4. So that's the next step. If the Hamming distance between our received code word and one of the 4 valid code words is, if the minimum of the distance is unique, then we'll assume that that's the received code word. First, look at the minimum distance. In this case, the minimum is 1. If it is unique, that is, there's only one valid code word with this minimum distance, and this is the case, there's only one value with a distance of 1, let's assume that the transmitted code word, I'll say we'll assume the transmitted code word was the code word which has the unique minimum Hamming distance from our received code word, which is this. We receive a code word, we compare to the 4 valid code words, whichever one is closest we'll assume was the original transmitted code word, but only if it's unique. That is, if there were 2 code words with a distance of 1, they are not unique, and we would not do this. In this case, there's 1 code word with a minimum Hamming distance of 1, and therefore we'll make the decision at the receiver to assume the transmitted code word is 00111 and simply map back to our data. We'll assume the received data, if this was the transmitted code word, the received data must have been 01. What happened? Transmitter transmitted data 01. We transmitted the data 0, 1, but in fact a code word. We had some bit errors, or 1-bit error. The receiver detected that error because we received an invalid code word, made an assumption about what the transmitted code word was. It chose the valid code word which was closest to the received code word, and therefore made an assumption about what the received data is. It assumes the received data is 0, 1. This is error correction, or forward error correction. We had an error, we corrected it, because in fact we've received the correct data now. So this has been successful. That's a bit more complex than the parity check. So there may be some more questions. Okay. A summary of what happens at the receiver is here. If the received code word is invalid, assume the valid code word, that is the unique minimum Hamming distance from the received one, was transmitted. That's what we did here. Find the closest valid code word to this. The closeness is measured in the Hamming distance. We found this code word to be the closest, therefore assume that was transmitted and assume that's the corresponding data. This is good practice for the exam. Third case. Try it now. First and fourth bit are transmitted in error. Bit 1 and bit 4. There are 2-bit errors. Find out what the receiver does. And to get you started, if the first and fourth bit are transmitted are in error, then what we would receive, the received code word, would be 10101. That's the received code word. What does the receiver do in this case? Try and calculate what the receiver does. Okay. Is the received code word valid? If not, find the closest valid code word.
Why receive code word is that it's not like this. 1 and 4 is error, so change.
No, this is bit 5, this is bit 4.
Before.
1, 2, 3, 4.
Oh, okay, okay.
first and fourth bit. Because it's the corresponding data for this code word from the table. I'll see it again. Okay, was it valid? Received code word? It's invalid. So if it's invalid, we detect an error. So we've got error detection here. That's been successful because there were errors. We detected the error because it's invalid. So once we have an invalid code word, we compare it to the valid code words. And I'll show that on the screen again. Hamming distance between our received code word and the first? Anyone? 3. Between the received and the second? 2. Received and the third? 4th? Do we have a unique minimum? The minimum is 2, but it's not unique. This means that our received code word is equal distance to these two valid code words. In this case, we cannot correct the error. We don't know which one. We can't make a guess. It's a computer. We don't know which one is, or we don't have a probability that one is more likely to be transmitted than the other. So we detect an error, but we cannot correct. Let's just summarise. That's it, we're finished at the receiver. We detected bit errors, but because we did not have the unique minimum distance, we couldn't make an assumption as to what the transmitted code word was. We think the transmitted code word is either this one or this one. And since we don't know which, we end there and simply say that error detected but not corrected. We would need some other mechanism to correct in this case. So we've seen 3 different outcomes. The first case, everything was fine. We received a code word which was valid. The second case, we received a code word which was invalid. We detected an error. And because that code word was close to one of our valid code words, we actually corrected that error and received the correct data. And then in the third case, we detected an error, but we didn't have enough information to correct that error. So in an error correction scheme, we can detect some errors and correct them, or detect some and correct. And in some cases, we can only detect but cannot correct. And there'll be some cases that we cannot detect. Same with our parity check. We saw cases where there were errors, but we did not detect them. The same can apply here. If you try different combinations of errors, you can see the different outcomes that may happen at the receiver. And that's good practice to understand how Hamming distance and how the forward error correction works. Finish for today. Tomorrow morning, at the start of the lecture, we'll have a quiz. It will not cover this. It will cover. There are 3 questions. They're from signal encoding and I think something about transmission media. And then we'll just summarise and finish on this and then talk about the midterm exam tomorrow and go through practice for the exam.